Hi guys and welcome to this my video on similar figures, part of the Year 11 General Maths course here in Australia. And if I'm honest with you, one of the most annoying parts of this course. That doesn't mean you get to stop now. Come on, stick with me. My name is Darren from Maths Guru. Thank you very much for watching. Hopefully you are going to find this useful. Now before I get into this, I always ask the same thing. How are you? No, I mean obviously I want to know how you are, but I'm going to ask you, can you subscribe to my YouTube channel? Again, this is the needy part of the video. There should almost be angels weeping in the background, but if you can subscribe to my YouTube channel, it just tells me that people out there are watching. All right, again, as I've said so many times, I think my mum is on about her 7,000th subscription to YouTube. All right, thanks mum for watching and making me feel loved. If you can join her, that would be great. Right, it means the world to me if you actually subscribe. If you haven't done that, don't worry about it. I'll forgive you this time. Now, what are we going to work through? Normally I'd read through that, but you can pause the video if you need to and actually have a look. It's just basically what I said on the tin. We're going to look at similar figures. Now, this is moving through the chapter for the Cambridge books, and thank you very much, Cambridge, for letting me use it at a bit of a rate of knots, right? There's a lot of stuff in here that you really do have to practice, right? We've dealt with, what did I deal with in the last times? We dealt with surface areas, we've dealt with volumes, we've dealt with so much stuff. Similarity is actually quite simple, all right, because it's basically saying how many times bigger or smaller is one shape than another, all right, which is pretty good to do, and that's what we're looking at here. So I say here it's not always about size, and we'll leave that one there because if I've got boys in my classroom, they always giggle, which is a little bit silly, really, isn't it? But anyway, all right, this section of the course is actually all about size, and if we look at the rectangle shown here, I'm going to ask you if I can. I'm going to tell you they're actually similar. So they are what we are called similar. All right. Now in maths, that basically just means that what I've done is I've taken this rectangle here and probably done something to it to turn it into the second rectangle here. Now you're probably turning around and going, "You've doubled it," and I'm like, "Yeah, congratulations." And that's what similarity is. I have taken every side length of this rectangle here, and I've times it by 2. Now, if I hadn't times it by 2, if, for example, I had got a rectangle like this, where that was 6 and that was 2, then they wouldn't be similar. So these two these two rectangles here wouldn't be similar. Why not? Because I've not multiplied every side length by the same number. Here, I've obviously times by 2, but here I've kept it the same. So goodbye rectangle, you is no good to me. All right, now again, I know from maths that because my maths is pretty good for my 2 times tables, I've actually times that by 2, yeah? And I know that to go from 2 to 4, I've also times by 2. But what if they give me crazy numbers? There must be a way to find out this scale factor of enlargement. Oh, hold on, throwing in some language there. So scale factor of enlargement is what we call it in the United Kingdom. And that's basically this multiplier here. By how many times have I enlarged one side to get to the other? All right, so that's why we call it the scale factor enlargement. If I use that, don't get confused. It just means that's the multiplier I've used. Rightio, but is there a quick way of doing it? Well, yeah, in many cases, what we can actually do is we can take the side we've gone to and divide it by the side we started with. So if I look at that and I do 6 divided by 3, what do I get? I get 2. Does that work? Yes, I've got 4 divided by 2. So I've got my 4 on my bigger one, 2 on my smaller one. Divide those together, gives me 2. And so long as I do that, if I can take every sort of joining side or similar side or, you know, like side and divide them, then it's awesome. But I've got to make sure that I always do the one I've gone to and divide it by the one I started with. Well, there's got to be language that's better than that to use. Well, actually, as it turns out, yup, there is. We would call this one here the image, and this one here the original. All right, so the one you're going to, I call it the image. The one you're starting with, you look in the mirror, I'm pretty much me. But that dude who's talking to you in the corner at the moment, which is also me, is my image. Yes, and I'm so sorry the way I look. Genetics, can't help it. All right, but the point of it is, if I want to find out my scale factor of enlargement, I just take one side length of my image, and divide it by the side length, the same side of my original. We'll come back to that in a moment, yeah? And again, the trick to this question here is, though, that for this to be a scale factor, we have to make sure that the angles inside stay the same after enlargement. And again, a lot of people get very tricked there. It's a bit of a trick, because if I make a rectangle twice as big, for some reason, some people out there think that the angles inside would grow twice as big as well. Okay, let's just unpack that one for a moment. That's 90 degrees. That's 90 degrees, that's 90 degrees, that's 90 degrees. So all of the angles in there added together give me 9, 18, 36. So 360 degrees. If we're going to make a rectangle bigger, I still need to make it a rectangle. So it wouldn't make any sense for the angles inside that rectangle to add up to 720 degrees. So the angles actually, when you make things larger, don't change. That includes in triangles, right? Big trick here. Right, so here we go. For your summary notes, and again, guys, hopefully you're aware that you can go to mathsguru.com, sign up for absolutely free. You can get downloadable notes. These lessons all, put in nice orders, VCAR questions, the works. Have you told your teachers and your friends about it? No? Please do. If you're subscribed, please do. So here we go. And I know because lots of people out there like formulas, the ratio of enlargement, all right, or the scale factor of enlargement is the side length of the image. I just said that. Choose one side of your image and divide it by the same side length of the original. So again, 4 divided by 2. Always make sure that you label your image and your original. And then it should be child's play. All right, now, so what about the ratio of the areas? Well, surely if I double the lengths, I'm just going to double the areas, aren't I? I mean, that's gone 3 to 6. That's gone 2 to 4. So don't the areas just double? Bit of a trick. All right, so let's see what actually happens. The area here is given by 3 times 2, which is 6 centimeters squared. Ka-ching. Thank you very much. Nice and easy. So the area of the next one is going to be 12, yeah? Nope. So the area is given by 6 times 4 there, which is 6, 12, 18, 24 centimeters squared. Hold on a moment. How many times bigger is that? I've gone from 6 to 24. Well, if I do 24 divided by 6, much like we did before when we did a side length divided by the same side length, if I do the area divided by the area, I actually get 4. So the area has actually grown 4 times. Why on earth would it grow 4 times? Well, I sort of tried to give you a bit of a hint a minute ago. How many times did that grow? That one side length grew by 2, didn't it? Yeah? And how many times did that side length grow? Again, by 2. And what is 2 times 2? 4. And basically, that's the trick to the whole thing here. If I multiply one side length by 2, and I multiply the other side length by 2, then I've effectively done my area 4 times bigger, because 2 times 2 is 4. So if I know my scale factor enlargement, and I know whether I'm doing, or how many sides I'm multiplying, I can actually get my scale factor enlargement or my area. But there's got to be an easier way, because you guys love a formula. Of course you do. The ratio of areas is given by my scale factor of enlargement. Right? That's for one side. How much have I multiplied by to get to one side? And you simply square it, right? Times it by itself. So let's check with another example. Sorry about that. What do we got here? The ratio of the areas. Well, let's just check first that this is actually a similar figure. The reason we're going to check it's a similar figure, all the sides have to be multiplied by the same thing. So how have I gone from 3 to 9? Well, let's just check. I've done 9 divided by 3 is 3. Okay, that's good. Let's choose another 2 sides, 12 and 4. Is 12 divided by 4 3? It is. Whoa. All we've got to do now is check the last ones, 15 and 5. Is 15 divided by 5 3? It is. Because all of those sides have been multiplied by the same things, they are similar figures. Rightio. So let's see, what about our ratio of areas? Well, I could work out the area of each of them, but why would I need to do that now? I have my scale factor of enlargement. I know to go from one side to another, I'm simply timesing by 3. So therefore, my ratio of areas is equal to the scale factor of enlargement, which is 3, not times by 3, you don't need that, it's just 3, and then square it, which gives me 9, not 6, 3 times 3 is 9. So if I was now to work out the areas of each of these shapes, and let's just do that to check, the area of that first shape would be a half times 3 times 4, yeah? Remember, area of a triangle, half, base times height, so that's 3 times 4. 3 times 4 is 12, that's going to give me 6 centimeters squared. What about the area of the bigger one? It's going to be a half times 9 times 12. Sheesh! 9 times 12 is going to give me, yep, no, I can't do it in my head. I've got to calculate it. 9 times 12 gives me 108. Divide that by 2 is going to give me 54 centimeters squared. Shall we just check now my ratio of areas? How am I going to do that? I'm going to do 54 divided by 6. So 54 divided by 6 is 54 divided by 6, 9. And yay, that's what I was expecting. And I do not know what's just gone wrong with my voice. But there we go. So to make things easier for ourselves, if I know the scale factor of enlargement, I can square it, and that will give me the ratio of my areas, which actually I could go on and use. So here's some examples from the Cambridge Maths textbook. Thank you very much, Cambridge, for letting me use your examples. The rectangles shown are similar. All right, now when they are similar, it means that the multiplier from 5 to 25 and 2 to 10 is exactly the same. So let's find the ratio of their side lengths. We can do that. The ratio of side lengths. Now again, when it says that, it's just basically saying, take two similar side lengths and divide them. So which one's the original and which one's the image? Well, I'm going to suggest that that's the image just because it's called it rectangle B, and we'll call that one the original. So what I need to do now is take a side length of 10 and match it to the one on the other side of 2. So that's going to be 10 divided by 2, which gives me 5. So my ratio of side lengths is 5. I don't need the units because it's just telling me that that's times by 5. So that's my first dot point done. Fabulous. Ratio of areas. Well, again, once we know the ratio of my side lengths, which in this situation is 5, I simply square it to give me my ratio of areas, which gives me 25. And that means that the area of this one is 25 times bigger than the area of that one. And again, because I've multiplied that by 5, and I've multiplied that by 5, 5 times 5 is 25, just in case you wanted a different way. Now, here is a small curveball, and I said to be careful. The two shapes shown are similar. Determine whether the first shape has been scaled up or scaled down to give the second shape and find the scale factor area. So obviously the first shape here is my original and this here is my image. Well, hopefully everyone knows that if that starts as 3 and goes to 2, it's got to be scaled down. So I'm not even going to write that because that's just insulting my intelligence. Let's find the scale factor. Is going to give me, remember we choose the image, 2 divided by 3. So in that situation, it is just going to be 2 divided by 3. Now, I know a lot of people will fire up the calculators and put that into a decimal, which will give 0.6666666 to infinity and beyond. But the point of it is don't. Just leave it as it is. 2/3, more than happy to leave it as a fraction here than as a decimal. What is the scale factor of the areas? Well, again, once we know the scale factor for the lengths, we simply do the scale factor for the areas is equal to the scale factor for the lengths and squared. And again, you can put that into your calculator and square it. Hopefully, if your calculator's in the best mode, and that is an exact, it should come out as 4 on 9. Yeah, if your calculator comes out with 0.44444 reoccurring, again, probably not the best answer. But again, for those of you who are interested how that works, well, when you square something, what do you have? You have 2/3 times 2/3. And when you multiply fractions together, it's the easiest ones on the planet because you multiply the top numbers together, multiply the bottom numbers together. So 2 times 2 is 4, and 3 times 3 is 9, and ka-ching, life is good. Example 3. Find the value of x for the two similar triangles. Oh, and again, they're trying to sort of test whether you understand what similarity is. Now, we have gone, that is my start length, that is my end length. So we know that this has gone to this, and that has gone to this. So if I can find the scale factor of, and I use the word enlargement because it's gone smaller, but we still do that, then we can maybe use that. So I've got two side lengths I know. So I've got the 24 and 10. Which one is my image? We'll assume that one's my image. That one's my original. So my scale factor is given by the image length, which I'm going to use as 10, divided by 24. Now again, I could put that into my calculator and get some random decimal, but I'm going to divide both of those by 2 to give me 5 on 12. So there is my scale factor enlargement. Now what does that actually mean? It means if I take this 24 and times it by 5 on 12, I'm going to get 10. And you're going to say, why? Why? Let's go back. What was my scale factor enlargement here? It was 5. So if I took this side length here and multiplied it by my scale factor enlargement, I got to that side length there. If I did that side length there, 2, and multiply it by 5, I get 10. So that is my multiplier of how to get from one side to another. Well, I know I've got this side length here of 18. How am I now going to get that side length there? Well, I'm going to say that therefore x is given by the side length, which is 18, times by my scale factor of enlargement, which is 5 on 12. Let's fire up my calculator. Let's see where we can do this. 18 times 5 divided by 12. Hit enter, and that gives me 7.5 centimeters. So this very short chapter, and you're going to go, short, you haven't shut up yet. I know, all right, easy, Tiger. Yeah, but this very short chapter is just giving you all the different ways that using this areas and scale factors can actually help. Then we move on to map scales, which seems a little bit weird for this chapter, but basically it's the same idea. And a lot of people go, I don't understand map scales. Well, that's probably because you don't even read maps anymore. It's all on your GPS and on your Waze and your Apple Maps and your Google Maps, and it's all done for you. I swear computers are going to take over the world. It's a bit worrying about AI. Anyway, right, so a scale has a map of 1.20,000. Let's understand what that means first. 1.20, 1, 2, 3. What it means is that for every 1 unit of something on a map or on a scale, it's equal to 20,000 of those in real life. So, for example, if I had a map, it would say that 1 centimeter on the map actually in real life stood for 20,000 centimeters. So obviously that's why we have maps and scales. Because if I went into my GPS, if I went into Google Maps, and I basically was like, oh, take me to, I don't know, Alice Springs or Geelong or something, and it was real size, it wouldn't fit on my, could you imagine the size of my display on my car? It'd be nuts, I might as well walk. But that's why they scale it down. But they tell us that 1 centimeter in real life is 20,000 centimeters 1 centimeter on my map is 20,000 centimeters in real life. But again, it doesn't have to be centimeters. Believe it or not, I can actually use millimeters. So 1 millimeter on my map is equal to 20,000 millimeters in real life. Or if I was really nuts, 1 meter on my map is equal to 20,000 meters in real life. So the units are interchangeable and will generally be given in the question. So if the measurement on the map between two towns is 5.4 centimeters. There we go. So that's the important part of my question, centimeters. So now I'm going to write centimeters above there and centimeters above there. Right, what is the actual distance? So they've given me the map distance. So I now know that I've got 5.4 centimeters on my map. And I'm going to try and work out what that means in real life. Well, how have I gone from 1, or what's the easiest way to go from the number 1 to 5.4? And if anyone out there says add 4.4, I'm going to cry. Nope, I can multiply. So in that situation, I would multiply by 5.4. Well, we know with similarity and scale and all those things with multipliers, what we do to one side, we have to do to the other side. So I'm going to multiply that by 5.4 as well. Fire up my calculator. Let me see what we've got. 20, 1, 2, 3, times it by 5.4, hit enter, and we get the staggering number of 108,000. And I finished the question. Yes, that was easy. Nope. Because the question basically went on to say, and this is where the trick was, give your answer in kilometers. Shucks. Now, obviously, that is in centimeters. So then we would have to use the next section of mathematics and go, well, how do I get from centimeters to kilometers? Well, we know that if we want to go from centimeters to meters, you divide by 100, and this should be in your summary book. Yes, and meters to kilometers, you would divide by 1,000, right? So these sort of conversion things should be in your calculator, or sorry, in your summary book. So I'm now going to do 1080. I'm going to divide that by 100, and then I'm going to divide it again by 1,000. So let's do that. So I know of character, so I'm going to divide that by 100. I'm going to divide that by 1,000, and there we go. I get the staggering value of 1.08. So therefore, yes, the distance between the two towns in real life is 1.08 kilometers. All right, so again, there's a lot covered in this particular section of the course. Whew. And hopefully it has made sense to you. Rightio, we're pretty much done for this video. Thank you very much for watching. About 21 minutes again. Shucks, always about 20 minutes. Hopefully you found it useful. If you have, do me the favor and subscribe to my YouTube channel and let your mates know and your teacher that this resource is out there and is actually, hopefully, really, really helpful. I'll see you in another video. Take care and please stay safe.